Hello students, in this video we'll introduce the Laplace transform and see examples of how we can compute the Laplace transform of certain functions. The Laplace transform of a function f of t is defined by the following formula. F tilde of s is the integral from 0 to infinity of my function f of t, which is given to us, e to the negative st dt. So notice when I take the Laplace transform of a function, I not only change the function, I change the independent variable as well. So my function t and f is transformed by this Laplace transform to a function of a new variable s and a new function f tilde. So let's see several examples of how we can compute the Laplace transforms of functions. So we'll start with the most basic example. If I look at f of t, which is identically equal to 1, we can find its Laplace transform using this formula. The Laplace transform of this function, f tilde of s, will be the integral from 0 to infinity of 1, my function is identically equal to 1, e to the negative st dt. So I can integrate this. This will be e to the negative st over negative s, because my integration comes with respect to t. And I evaluate this from 0 to infinity. Well, when I plug in infinity to e to the negative st, I will get 0 as long as s is positive. So I would like this s, I'm going to assume that s is positive over here. And if s is positive, e to the negative st, when t tends to infinity, will tend to 0. So the top limit will be 0. And I'll subtract the bottom limit. When I plug in t equals 0, I have e to the 0. E to the negative s times 0 over negative s will be my bottom limit. And that will simplify to 1 over s. In other words, the Laplace transform of the function 1 is 1 over s, provided s is strictly greater than 0. So one thing to notice is that the domain of f was all real numbers, and the domain of f tilde is all positive values of s. So my function changes. My function changes from 1 to 1 over s, and my domain changes from all real numbers to only the positive real numbers for my Laplace transform. Let's see a second example of this. If I look at the function f of t is e to the at, we can find its Laplace transform by using this formula. The Laplace transform of e to the at is the integral from 0 to infinity of e to the at, that's my function, e to the negative st, that is called the Laplace transform kernel, dt. And this will also be easy to integrate with respect to t. It'll be e to the a minus s t over a minus s, and this will be evaluated from 0 to infinity. Now, we notice that this first limit of t equals infinity will be equal to 0 if a minus s is positive. So, if a minus s is negative, rather, I will have that a minus s less than 0 will mean that the infinite limit is 0. So I will assume this condition, and my top limit will be 0. I will then get, this will be 0 minus e to the a minus s times 0 over a minus s. And when we simplify this, I will have 1 over s minus a, as long as s is larger than a. So again, my domain has been restricted by taking the Laplace transform. Now, what we can do is we can actually apply this formula when a is a complex number. So what we can now do is we can say, I can apply the previous result to say that f of t is cosine of t, which we know by Euler's formula is e to the I t plus e to the minus I t over 2. So when I Laplace transform this, f tilde of s will be the Laplace transform, 1/2. I'll pull that out. The Laplace transform of e to the at is 1 over s minus a, so I'll have a 1 over s minus I plus 1 over s plus I, which when we simplify will be 1/2. I will have an s plus I, and I'll have a plus s minus I over s squared, and then I have a negative is and a positive is. Those will cancel, and I have a negative I times negative I, which will be a positive 1. So if I simplify this, I will have a 2s on top, divided by 2 will be an s, over s squared plus 1, which is the Laplace transform of cosine. Now the final example we'll see will be useful when we want to do the inverse Laplace transforms, or when we find the Laplace transform of a Taylor series. So the final example of computing Laplace transforms will be f of t is t to the n. If I Laplace transform this, the Laplace transform of this function will be the integral from 0 to infinity of t to the n, that's my function, e to the negative st dt. Now what we'll do is we'll make a u substitution. What we will say is we will say, let me let u be s times t. That will tell me that du is s dt. And my limits will stay 0 infinity. So my limits will stay the same. When I make this substitution, I will see this is the integral from 0 to infinity. T is now replaced with u over s. So I'll have a u over s to the power n. Then I'll have an e to the negative u. And then I'll have a du over s. So if I count the number of s's I have, I'll have n s's over here, and I'll have 1 s over here. So I'll have a 1 over s to the n plus 1, the integral from 0 to infinity of u to the n e to the negative u du. And we can do some calculus, and we say that this integral over here is exactly equal to n factorial. So my Laplace transform of t to the n is n factorial over s to the n plus 1. So these are several common examples of Laplace transforms, and we'll see in subsequent videos how we can use these results to solve differential equations, to solve systems, and to solve other problems. Thank you very much.